Good day, everyone. I'm Arvin Enriquez, your subject teacher in General Mathematics. With this video lesson, we're going to discuss the topic intercepts, zeros, and asymptotes of exponential functions under your General Mathematics from Quarter 1, Module 21. Our lesson objectives. At the end of this video lesson, you are expected to determine zeros of an exponential function. Second, determine intercepts and asymptotes of an exponential function given the graph of an exponential function. Let's now deal with the intercepts, zeros, and asymptotes of an exponential functions. So in the previous lessons, you learned how to determine domain and range of an exponential function. So this domain and range, this will be your independent and dependent variable that you can see in your exponential function, or that will be your x and y variables in your exponential function. You were to only consider cases of exponential functions where p of x is linear. So your p of x, or the function of p with respect to x, is linear. In which case, your b now raised to p of x, or the function of p with respect to x, will always be defined for any value of x. Yes, it is, no? Because any value that we're going to put as a value of x, then it can give you a value of your function. So thus, the domain of an exponential function is the set of real numbers of R, or R, meaning to say that the domain of any exponential function will start from negative infinity to positive infinity, including 0. So for the range, note that b raised to p of x is greater than 0 for any value of x. Hence, the range of an exponential function will depend on a and h. Yes, no? The behavior of your range in an exponential function will always be dependent on the value of h and a. So, law of exponents. So, for any real numbers a and b, so your a and b here is a real numbers, so it can be positive or negative, and any real positive numbers m and m, meaning to say that m and n are only positive real numbers. Now, let's deal with the law of exponent. For your first law, if there are two bases with different exponent here, and the operation between your two bases is multiplication, then we're going to copy your base, and we just simply add your two exponent m plus n. So that will be your first law. As long that we have your two or we have the same bases, no, in this case. For letter B, or your second law, your a raised to m, your exponent here is m raised to n. So we just simply multiply your m and n and apply it to your base a. So that will be your second law. So it's a different thing once there are two bases with two different uh, exponents. So we just simply uh, add your exponent if we have your two uh, if your two bases are the same values, meaning to say that we're going to add your two exponents attached to them. Now, for letter C, A and B, so there are two bases here, which is your A and B. So if we're going to simplify this one, so we just simply distribute this n as your exponent here to your A and B. So it becomes a raised to n and b raised to n. So that's how we apply your third law of exponent. And for letter D, or the fourth law, no, here there is an involvement of division. So as you can see, we have two bases with the same values, no, wherein your b, or your base 1, is equal to your base 2, where your a is your base 1 raised to m, and your base 2 is also equal to a raised to n. So if that is the case, no, if the operation between your two exponential expression is division, we just simply copy your base and we subtract your exponent to your denominator to your exponent in your numerator. As long that we satisfy this condition that your a is not equal to 0. Why is that? Because if a is equal to 0, it makes your fraction, no, undefined. So it makes your fraction undefined. That's why we really need to make sure that your a is not equal to 0. Now for letter E, or the fifth law of exponent, your a over b raised to n, once we're going to simplify this one, it's the same thing with your letter C. So we just simply distribute your n to your numerator and to your denominator. So that's why it becomes a is equal to a raised to n over your b raised to n. As long that we satisfy again the given condition that your b is not equal to 0, because it makes your fraction undefined. And for the last law that we're going to deal for this module, and that will be your a raised to 0 is equal to 1. Meaning to say that this a, no, is a real numbers. These are real numbers raised to 0. If a real numbers raised to 0 is equal to 1. So if we satisfy that condition, then the value for this one is equal to 1. Now let's deal now with the examples that we're going to apply your law of exponents. Here we're asked to simplify each expression and express the answers with positive exponents. So your first example here, we're going to apply your law of exponent, wherein if you try to assess and look at your bases, no, your base 1 here is x, your base 2 here is also x. Meaning to say that your base 1 is equal to your base 2, so we just simply copy your base. Here, there is an operation here between your base 1 and base 2, which is multiplication. That's why we can arrive to an idea that we're going to copy your base and we add your two exponents. That's why we copy your base here, then we add your two exponent here, which is your 3 and 5. So your final answer now is x. Then if we add 3 to 5, that will be equal to 8. So our final answer is x raised to 8. Now for number 2, it's another law of exponent that we're going to apply. Here, there is an x minus, raised to negative 2 raised to 3. So when you say outside your parentheses, there is an existing exponent which is equal to 3. Now, there is only one base here. That's why we copy your base, then we multiply your two exponent. So your two exponent here is negative 2 and positive 3. So negative 2 multiplied by positive 3, so that will be equal to negative 6, and we copy your base. Now, as you try to look at this one, your exponent here is negative. So this negative exponent represent that this term, no, with your base x is at your denominator. So if we're asked to convert this x raised to negative 6 to a fraction, So we're going to put this x, no, minus 6, no, to your denominator, and we multiply your exponent to negative 1. So it becomes 1 over x raised to 6. Again, if you're asked to convert this x raised to negative 6 to a fraction, or if you want this x raised to negative 6 uh, to have a positive value of exponent, we just simply move no, this x raised to negative 6 from numerator to denominator, and we multiply your exponent by negative 1. So that's why your final answer here, no, from numerator to denominator, then we multiply your exponent here by negative 1. So that's why it becomes positive 6 in your denominator. Now, in the third example here, no, there is an exponent here, no, outside your parenthesis, which is negative 3. So inside your parenthesis, there's a 2x raised to negative 5. Your negative 5 here is your exponent only in your x variable x and not your exponent in your 2. Even if your 2 attached to your x, your negative 5 here is your exponent only in your variable x. Now, we just simply distribute this negative 3 as your exponent outside your parentheses to the two bases inside your parentheses. So it becomes 2 raised to negative 3 and x raised to negative 15. So in this case here, no, that negative 3 multiplied by negative 5, so it becomes positive 15. So here, as you can see in this part, no, so we just simply, no, if this is the case, they are both in the numerator. In reality, there is one here as your denominator. So these 2 raised to negative 3, we're going to move this term to your denominator for us to have two exponents that are positive exponent. So because our target now is to have a positive exponent. That's why we really need to convert. If there is a negative exponent in this case, in your numerator, then we just simply move it to your denominator and multiply your exponent by negative 1, I mean. So here, right after we convert this one, so still at your numerator, there is an x raised to 15 because that's a positive exponent. What we need to do is to move your 2 raised to negative 3 to your denominator to make your exponent positive. Then next, for us to simplify, then we copy your numerator, which is x raised to 15. So your 2 raised to 3 is equal to 2 times 2 times 2. So it becomes positive 8. So your final answer now is x raised to 15 over 8. Now let's deal with the property of equality for exponential equation. So an exponential equation is in one variable is an equation where the variable is an exponent. Yes, it is. No, there is only one variable involved in your exponential equation, and that is your x variable. In solving exponential equations, the property of equality for exponential equation, also known as equating exponents property, implies that if the bases are equal, the exponents must also be equal. That's why we really need to make sure that your two bases are equal. Or if the given, no, if the scenario is that if there is a given and your base 1 is not equal to your base 2, now our next move is to convert your base 2 as the same how we express your base 1 to make your base 1 equal to base 2. Now we're looking to an exponent, no, of a base 1 that can provide you the same value of your base 2. So we're going to express this base 2 as the same with your base 1. And for us to conclude that your exponent 1 is equal to your exponent 2, we must deal, or we really need to make sure that your base 1 is equal to your base 2. So this could also be stated as follows. If A, B, and C are real numbers, A is not equal to 0, supposed to be, so you need to consider and satisfy this condition that your A raised to B is equal to A raised to C if and only if your B is equal to C. Yes, it is no. We can assume that your exponent 1 is equal to exponent 2, which are B and C here. No? If and only if your base 1 here is equal to your base 2 here. If that is the case, then we can assume that your exponent 1 is equal also with your exponent 2. So for the examples, so solve for the value of the variable that would make the equation true. Now, there's a given here. So since the bases are equal, as you can see, your base 1 is equal to 2, and your base 2 is equal to 2 also, then the exponent must be equal to. So we can assume that your x now is equal to 4, or the value of your independent variable here, which is your x, is now equal to 4 because your base 1 is equal to your base 2. So since x is equal to 4, let's make uh, some checking, no? So we just simply substitute your 4 as the value of your x, and let's check if it can provide you the same value as your right side of this exponential equation. So if we substitute this 4 to your x here, it can provide you 2 raised to 4, which is now equal to the right side of your exponential function. So therefore, the value of your x here is a correct value, no? It is a correct value. Now, for number 2, 3 raised to 4y. Here in your exponent, no? In your definition of your exponential equation, there's only one variable involved. It can be x, y, or any letter can be used as an exponent here, as long that we know that this exponent represents a variable, no? As long that there is only one variable involved. So since the bases are equal, as you can see that your base 1 is equal to 3, your base 2 is equal to 3 also, then we can assume that 4y now is equal to 16, or simply your exponent 1 here is equal to your exponent 2 here. For us to get the value of your y, we just simply divide the entire equation by 4. So your 4 here will be cancelled out in your left side, so it becomes y. Then 16 divided by 4, it becomes 4, because 4 and 4, 16 divided by 4, 16 is a number which is divisible by 4, so we can divide 16 by 4, so it becomes 4. That your y now is equal to 4. Now for us to check, no, we just need to substitute this value of y to your left side. So it provides you 3 raised to 16. So it's the same value with the value at the right side of the exponential equation. Now for number 3, since the bases are equal, so we can assume again that your exponent 1 is equal to your exponent 2, which is x minus 2. So we just simply transfer or transpose this negative 2 to another side of your equation. So from negative to positive, so 6 plus 2, so it becomes 8. So we copy your variable x from one side of your equation. So the value of your x now is equal to 8. So it's the same thing, no? On how we check. So we just simply substitute this one to your right side, to your x variable in your exponent 2. Then it becomes 8 minus 2, so it becomes 5 raised to 8 minus 2 or 5 raised to 6. So it's the same value with this uh, left side of your equation. So let's deal now with determining the zeros of exponential equation. So the zero of an exponential function refers to the value of the independent variable x that makes the function zero. Now, what is the value of x that makes your function equal to zero? And that will be your zero of an exponential function. So graphically, it is the abscissa of the point of intersection of the graph of the exponential function and the x-axis. Yes, it is, no? Because if there is a given value in your x-axis, there is no y-coordinate. Once the point of intersection falls exactly in your x-axis, because there is no vertical distance from your x-axis, meaning to say that your y is equal to 0, and therefore it's automatic that the function there, no, that the value of your function f of x in that point of intersection is now equal to 0, because that point of intersection falls exactly, no, at your x-axis. So there is no y-coordinate for that point. There's only x-coordinate, meaning to say that there is a horizontal distance from your y, but there is no vertical distance from your x, because it falls exactly, no, in your x-axis. So to find the zero of an exponential function f of x, equate f of x to 0 and solve for x. So for example, so determine the zero of the given exponential function. So your given is f of x is equal to 3 raised to x. Now in this case, we're going to equate your given function, no, to 0 and solve for the value of x. That's why it becomes your f of x is equal to 3 raised x is equal to 0. So if we copy this one, so it becomes 3x is equal to 0. Now, the resulting equation suggests that f of x has no zero, since no real numbers of x will make 3 raised x is equal to 0 a true statement. Meaning to say, no, there is no value of x or real value of x that can provide you equal to 0 here. So if we substitute a value on this variable, so it can be 1, 2, or any negative numbers, there is no such thing, no, that this value of your left side can provide you a 0, even if we put any values of x on it. If that is the case, no, if we put negative, 0, and positive numbers, so there is no such thing, or there is no uh, way, no, for us to arrive that this value is equal to 0. Meaning to say, it makes your statement here a false statement, because 3 raised to x, and if we put a values on x, we cannot provide 0. So meaning to say that your left side is not equal to your right side, then there is no 0 for this exponential function. Now, for example number 2, your g of x is equal to 5 raised to 3x minus 12 minus 1. So for the solution, so to find the zero of the function, equate it to 0 and solve for the x. So it's the same process with your example number 1. So we just simply equate the function to 0 and solve for the value of x. Here, that's why your g of x now is equal to 0, and it makes sure 5 raised to 3x minus 12 minus 1 is equal to 0. So in this case, we just simply transpose or transfer this negative 1 to another side of your equation. That's why it becomes 1 raised to 5 raised to 3x minus 12. In this case now, no, in this case, your 1 here, we can provide this one in a form that we apply your a raised to 0 is equal to 1. Now, we can say that this law of exponent can be expressed to 5 raised to 0 is equal to 1 also. That's why we can rewrite this one, no, to 5 raised to 0. And to make sure that your bases here is equal to this bases. Or we can, because our main target or our main goal now is to make your base 1 equal to your base 2. Now, we're looking for a value or a base which is raised to 0 that can provide you 1, and that is 5 raised to 0. Because 5 raised to 0 can provide you 1. Now, in this case, no, since your base 1 is equal to your base 2, then we can assume that your exponent 1 is equal to your exponent 2. Now, in this case, we're asked to solve for x, then we transfer this negative 12 to another side of your equation, so it becomes positive 12, and we copy your 3x. If we divide both sides by 3 here, for us to cancel your numerical variable in this left side, numerical coefficient, I mean, in your left side, so we just simply divide the entire equation by 3, so it makes your resulting value x is equal to 4 because 12 divided by 3 is equal to 4. So your final answer now is x is equal to 4. So therefore, the zero of your g of x is now equal to 4. So that will be the value of your zero of an exponential function or the given exponential function. Now, for example number 3, your h of x is equal to 1 half raised to 3x plus 5 minus 8. So to find the zero of the function, equate it to 0 and solve for x. That's why your h of x now is equal to 0. Then it becomes 1 half raised to 3x plus 5 minus 8 is equal to 0. So we just simply transfer this negative 8 to another side of your equation, so it becomes positive 8. So we copy 1 half raised to 3x plus 5. Then now, we're going to look for the value or the base of a base 2, no, that can provide you a value of 8. So we can rewrite this one as 2 multiplied by 2 multiplied by 2, or we can rewrite this one as 2 raised to 3. That's why your 8 here becomes 2 raised to 3. Now, in this case, since your 2 is in your denominator, so we're going to move, no, or transfer your 2 here from your denominator to your numerator by simply multiplying the exponent of 2 by negative 1. So that it becomes 2 raised to negative 1 raised to 3x plus 5 is equal to 2 raised to 3. So as you can see, your base 1 here is equal to 2, and your base 2 here is equal to 2 also. That's why your base 1 is now equal to your base 2. So we can assume that your exponent 1 is equal to your exponent 2. So we just simply distribute this one, negative 1 to 3x, negative 1 to 5, so it becomes negative 3x and negative 5. So we copy your exponent 2, which is 3, then simplify. So we just simply transpose this negative 5 to another side of your equation, so it becomes positive 5 plus 3, so it becomes 8. And we copy your negative 3x in your left side. So for us to simplify and for us to get the value of this x, so we divide the entire equation by negative 3. For us to cancel your numerical coefficient in your left side, which is negative 3, then it becomes x is now equal to negative 8 over 3. So the zero of h of x is now equal to negative 8 over 3. Let's now deal with the intercepts of an exponential function. So the y-intercept is a point at which the graph crosses the y-axis and the x value is always at 0. It's automatic that when you're dealing with your y-intercept, your x value is equal to 0. It's the same thing with your x-intercept. Once you're dealing with your x-intercept, your y is always equal to 0. So when you want to find the intercepts from an equation, let the y value equal to 0, then solve for x. So it's the same thing with your y-intercept. Now, For examples, no? Your example, number 1. So find the x-intercept and y-intercept of y is equal to 4 raised to x plus 1 minus 2. So to find the y-intercept, let x is equal to 0. So we're going to assume that your x variable is equal to 0. Then by the substitution, we have now your y is equal to 4 raised to 0 plus 1 minus 2. So you're by simplifying, no? You're by simplifying, your y is equal to 4 raised to 1 because 0 plus 1 is 1. We copy your negative 2. So it becomes 4 minus 2. That's why your y is equal to positive 2. So your y-intercept for in this case is at 0 and 2. Again, once you're dealing with y-intercept, it's automatic that your x variable is equal to 0. There is only a value on your y. So with your, if you're dealing with y-intercept, you're just dealing, no, on looking for the value of y because your x variable it's automatic equal to 0. So to find the x-intercept, let y is equal to 0. Then by substitution, we have your y is equal to 0. In this case, is equal to 4 raised to x plus 1 minus 2. And then next is to transfer your negative 2 to another side, so it becomes positive 2 is equal to 4 raised to x plus 1. Now in this case, we're going to express 4 in terms of 2. So what will be the exponent of 2 that can provide you 4, which is 2 raised to 2. So we can express your 4 in terms of 2. So therefore, your base 1 now is equal to your base 2. So in this case, no, we can assume that your exponent 1 here is equal to your exponent 2 here. That's why it becomes 1 is equal to 2 multiplied by x plus 1. Next move is to copy your 1 at your left side and you distribute 2 to your x and to your positive 1. So it becomes 2x plus 2. In this case, we're going to transfer your 2 to the left side of this equation. So it becomes positive 2 to negative 2. So 1 minus 2, it becomes negative 1. We copy your 2x. So for us to get the value of your x, we just simply divide the entire equation by 2. So for us to cancel your numerical coefficient in your right side of your equation, no, we can cancel your numerical coefficient at the right side of your equation, which is 2. So it becomes x is now equal to negative 1/2. So meaning to say that the x-intercept now is equal to negative 1/2 and 0. Again, it's automatic. Once you're dealing in your x-intercept, your y is always equal to 0. For example number 2, find the x-intercept and y-intercept of your y is equal to 2x, 2 raised to x minus 64. So for the solution, so to find the y-intercept, it's automatic that we're going to conclude that x is equal to 0. Then by substitution, we can find the value of your y. Now, if we substitute your 0 as a value of your x variable here, so it becomes 2 raised to 0 minus 64. Applying your law of exponent, your 2 raised to 0, since 2 is a real number, then that is equal to 1 minus 64. Then your y now is equal to negative 63. So the value of your y-intercept, it's automatic that your x is 0 and the value of your y is negative 63. So that will be for your y-intercept. So for your x-intercept, we're going to conclude that your y is equal to 0. Then by substitution, we have your y now is equal to 0. Then we copy your 2x minus 64. We're going to transfer this negative 64 to another side of your equation, so it becomes positive 64 is equal to 2x. So if we're going to express this 64 to 2 as your base 2, no? What will be the exponent of 2 that can provide us 64? And that is 6 in this case. That's why 2 raised to 6 is equal to 64. is now equal to 2x. Since base 1 is equal to your base 2, we can assume that your exponent 1 is equal to your exponent 2. That's why the x-intercept is at 6 and 0. It's automatic. Again, once you're dealing with your x-intercept, it's automatic that your y is equal to 0. So let's deal now with the asymptotes of an exponential function given by a graph. So a line that a curve approaches arbitrarily closely is an asymptote. Again, but there is no point of intersection between your graph and your asymptote. So an asymptote may be vertical, oblique, or horizontal. As for this topic, horizontal asymptotes correspond to the value the curve approaches as x gets very large or very small. So with the help of the table of values and a graph, you can determine the asymptotes of an exponential function. Let us first take a look at the properties of function f of x is equal to 2 raised to x. So in this case, your a is equal to 1, your p of x is equal to x, and h is equal to 0. So assign integer values to x and find the corresponding values of f of x. And for x is greater than or equal to 0, meaning to say that the minimum value of your x here is equal to 0, and the maximum value up to the last value that is greater than, no, that are greater than your 0. Because the value of your x, we need to satisfy, no, that the value of x is greater than or equal to 0. As you can see here, no, please do take note that as x increases, the value of fx keeps on increasing rapidly. So as you can see here, from 0 to 9, so there's an increase in your x, no, definitely, as you can see on the table. So once your x increases, it's automatic that your f of x or your y keeps on increasingly rapidly. So there is an increase, no, that we can map on each increase on your x variable. Meaning to say that each increase, no, in your f of x can be mapped to each increase also in your x variable or x values. That's why we can conclude now that if your x increases, it's automatic that your f of x also increases. Now for x less than 0, so the values of x now is less than 0, meaning to say these are negative numbers. When the value of x decreases, as you can see here, the value of your f of x also decreases. So if you try to observe, at least as it was being mentioned in this slide, no, observe that as the value of x decreases, the value of f of x decreases as well. Notice that when x is negative and decreasing, the value of the function approaches 0. Yes, it is, no, but there is no point of intersection, no, between your asymptote and your graph. So thus the graph has y is equal to 0 as a horizontal asymptote, no? But there is no point of intersection again with your graph and your asymptote. But the fraction of the function approaches 0, but there is no such thing that this function will pass through your asymptote. That's why there is no point of intersection between your graph and your asymptote. Note, you will learn more about graphing an exponential function or another module. So one property of the graph is that it passes that point 0, 1, or the graph has its y-intercept which is equal to 1. So let us take this next example. Suppose that f of x is equal to 2 raised to x plus 2. Our table of values in this case is as shown below. No? So let's try to use your x variable here, no? The values of your x variable. in your first row, it start from -3 to +3. Then your f of x, as you can see in this case, no? When your x increases, it's automatic that your f of x also increases, no? Comparing the two, we can see the graph f of x is equal to 2x plus 2. It shifted up by 2 units. That of f of x is equal to 2x on the graph. So your 2 units here will be dependent on the value on this term. If that is 2, then it shifted up by 2 units. If that is 3, the graph shifted up by 3 units. So it will be dependent on the value on this given function. Now let's deal with the graph. As you can see, it shifted off, no? 2 units from your original graph, which is f of x is equal to 2x, no? When it becomes f of x is equal to 2 raised x plus 2, no? Your original graph shifted 2 unit, no? 2 units up. So as you can see here, this will be your original graph, and if there's a f of x 2x plus 2 here, so the graph shifted 2 units up. So from the graph, you can see that the horizontal asymptote of f of x is equal to 2x is equal to y is equal to 0. Or we can say that this is your x-axis, while the horizontal asymptote of f of x is equal to 2x plus 2 is your y is equal to 2. So in this case, no. So there are two horizontal asymptotes. Here, the horizontal asymptote will shifted off, no, 2 units away from your y is equal to 2 from your asymptote in your original function. So to help you understand more on this topic, here are some more examples for you to try. Hint: observe the value of d in the exponential function f of x is equal to a multiplied by b raised to x plus d. So here, determine the asymptote of the following of f of x. So we're going to assume that your y, no, the solution of asymptote is at y is equal to 0. The solution of the asymptote for your letter B is y is equal to 2. It will be dependent on this one. So in this case, in your letter A, there's no such thing as the next term without your variable as your exponent. No, that's why your y is equal to 0. Then here, your asymptote is equal to 2. It will be dependent on your term in the given function. Here, the asymptote is y is equal to -5 because it is -5 here. No, that will be your asymptote. In this case, your y is equal to -2 from your letter D or your fourth example because here there's a 2 here. That's why it's -2. Now, for this one, you're in the fifth, no, example, it's the same example with your letter A. The asymptote is at y is equal to 0 because there is no such thing as next term, no, that there is no involvement of your x variable as your exponent. That's why your asymptote is at y is equal to 0. So did you get the technique? Now, if there are still confusing phrases to you, do not hesitate to go back once again and verify the answers. Don't be hesitate to ask for help from your teachers, no? You can ask me, no, if there is a question or if you want clarifications, no, for this topic, then you can ask me right away. So have a happy attitude to get you where you want to be. So for your activity, so you're asked to complete the table. So you're going to complete the table for your exponential function. You're asked to deal with your y-intercept, your zero, and your asymptote. So what will be the value of your y-intercept? You're going to assume that your x is equal to 0. Your 0 will be dependent to the value of x that can provide you a function which is equal to 0. And then your asymptote will be dependent to the value, no, next to your exponential expression. So this asymptote will be dependent on the term without an x or without an involvement of x variable as your exponent. So that will be your asymptote here. There's a three exponential function here, and you're asked to complete the table by simply providing the values of your y-intercept, your zero, and your asymptote. So thanks for watching. So please like, comment, and subscribe.